So hi everybody and welcome. Welcome to my home. The campus is closed for the foreseeable future, so I'll be making these recordings here. Okay, so hopefully you've watched the last two videos that I posted where we introduced the idea of the probability distribution for a variable that comes from a sample, what we call the sampling distribution. And what we looked at in the last one was the sampling distribution for x bar being the sample mean. And today I want to introduce another variable that comes from the sample, so let's get right into it. So this is going to be section 7.4 in our textbook, and it's the idea of proportions. And this is quite simply how statisticians talk about the percentage of a population or the percentage of a sample that has a certain characteristic. So this is how we talk about the percentage of a population or of a sample that has a certain characteristic in question, that has a certain characteristic, if I spelled that correctly. So some simple examples of this. Suppose we look at new car buyers and we ask, okay, well, what percentage or proportion of new car buyers finance their new car? Suppose that we ask the question about, well, what percentage of college students have a part-time job? Or maybe we ask the question, what percentage of people in a city rent their home or own their home? So these are questions about percentages, what statisticians call proportions. And as always, we're going to differentiate between a population and a sample. That should come as no surprise. So let's suppose that we're working with a population. Then we would be talking about the population proportion, which is simply the percentage of the population that has this characteristic. The notation here is a lowercase p. The calculation is quite simple. It's x divided by n. And we know from earlier work that capital N is our population size. And in this case, x is how many in the population have the characteristic that we're asking about. And it'll be really important to remember later on that x has to be a whole number. X is a count. It's the number of people or the number of things in the population that have the characteristic. More about that later. Okay, so if we're working with a sample, then we would be talking about the sample proportion. And as you'll see, the calculation is exactly the same, but the notation is different. And the notation is kind of fun here. So we still use a lowercase p, but we put a hat on it. And so this is pronounced p hat, which can conjure up some interesting images, but the calculation is exactly the same. It's going to be x divided by n. And as always, lowercase n is our sample size, and x is going to be how many in the sample have the characteristic that we're looking at. And again, it's going to be important to remember that this X is a count. It's a number. It has to be a whole number. So as always, one of the first challenges we face is with vocabulary. I sometimes joke that statisticians use the word proportion. Normal people use the word percentage. As far as I'm concerned, those two words are interchangeable. They're synonymous. They mean exactly the same thing. Now, some people might disagree with me on that, but that's the way that I'm going to go. Proportion, percentage, same thing. So let's go and look at some numbers here. So let me erase this. And as I may have already said, in these videos, I'm now working on a small board. And if I write something on the board and then immediately erase it, don't get bummed out. You can always pause the video and go back and see what I'd written. All right, so for this example, let's consider our class data set. So hopefully you have a copy of that. And the question that I want to ask is what proportion or percentage said that they smoke? So what percentage said they smoke? And let's take a look at, let's start with class A. That's on one side of the class data set. So for class A, if you look at that column titled smoke, you can count up the number of people who said yes, and you'll see that 5 out of 25 said yes, they smoke. So what that's going to do is we're going to take those numbers and we're going to turn them into this proportion or this percentage. And what we have to always keep in mind is, will this produce a population proportion, a value of P, or a sample proportion, the value of P hat? And as we've said many times, the class data set shall always be seen as a sample. So when I turn this into a proportion, it's going to be the sample proportion. So the notation is important here. This is going to produce a value of P hat. And it's simply going to be 5 divided by 25, which is 0.20, which is 20%. So what percentage said they smoke? 20% of them said, yeah, I smoke. All right, now let's go look at class B. So class B, on the other side of the class data set, if you go and you count up the people who said yes, you'll get 6 out of 25 said yes. So that will also produce a value of P hat. But in this case, it's going to be 6 divided by 25, which will be 0.24 or 24%. All right, now this should not surprise you in any way. A different sample produces a different value of P hat. Remember, P hat is a sample statistic. It's a variable. It can change from sample to sample. Take a different sample, you get a different value of P hat. That should not surprise you. Moreover, not only is it a variable, but it's a random variable because our sampling is done in a random way. So, so we now have a random variable, and we need to talk about some other ingredients here. So let me bring out a different example here. So let me get rid of this, and let's set up the following scenario. I'll do this as another example. So let's suppose we go to a college where 60% 62% of all students have a part-time job. Okay, so that is suppose we know that P is equal to 0.62. And I have to remind you that right now we're living in this fantasy world where we're pretending that we know everything about the population, and we want to talk about what should happen when we go to that population and do a sample. So we're pretending that we go to a college and we know that 62% of the students have a part-time job. So I'm going to go to that population, and suppose we take a random sample and compute P hat, the percentage for our sample. And then here's where the probability question is going to come in. It's very much like the question that I asked in the last lectures, is would you be surprised to get, and I'm going to put up some possible values of P hat. I'm going to put up some values of P hat, and we're going to talk about whether you'd be surprised to get these. Would you be surprised to do this random sample, calculate P hat, and get a 0.61? Would you be surprised to take a sample, calculate P hat, and then get a 0.64? Would you be surprised to get a P hat of 0.21? How about a P hat of 0.94? How about a P hat of 0.62? What about a P hat of 0.56? And what I want you to do is think about this for a little bit. I'm checking in with your intuition. All I'm looking for is a simple yes or no answer. Based on your intuition, would you be surprised, yes or no, to get these values of P hat? Now, if necessary, pause the video here, think about this for a little bit, and then come back with your yes or no answers. Okay, so would you be surprised to get a P hat of 61%? And I'm going to argue no, I would not be surprised, because I'm going to a world where 62% of the people have this characteristic. 61% sounds like a reasonable value of P hat. So I'm going to argue no, I would not be surprised if that happened. What about a P hat of 64.64? Sorry, that percentage symbol shouldn't have been there. 0.64, would you be surprised? And again, I'm going to, for the same reason, argue that no, I wouldn't be freaked out if I got a P hat of 64%. But now if I got a P hat of 21%, that's going to freak me out a bit. Because again, I'm going to a world where 62% have this characteristic. 21% seems really, really low. So if that happened for a simple random sample, I'm going to argue yes, I would be surprised if that value of P hat popped up. And for the same argument, this one right here is going to surprise me also, because it seems really high based on what I'm thinking I should get. Now, here's a key one. Would you be surprised to get a P hat of 62%? To a certain extent, absolutely not, because 62% of the people in this world behave this way, or at this college behave this way, or have this characteristic. So this is not going to surprise me at all. 56%? I don't know. It's on the low side, but is it reasonable I don't know. Intuition is not working for me here, so I'm just going to leave that as a question mark. We'll have to resolve that a little bit later. Okay, so here's what it comes down to. What we have here is the idea or the concept that p hat is a variable that can change from sample to sample. Moreover, it's a random variable because our sampling is done in a random way. So p hat is a random variable, and when you answer these questions yes and no, you're telling me that whether that value of p hat is likely or unlikely. So when you say no, I would not be surprised, you're telling me that those values of p hat are within reason. But when you say yes, I would be surprised, you're telling me that that's a value of p hat that seems really unlikely and not within reason. Same thing here, seems really unlikely. This guy right here, this is cool because this is the expected value, right? So when you look at this, you're saying, well, that's pretty much what I would expect to get if I go to a world where 62% have this characteristic. This one, I don't know, we're still out on that one. But do you see what we're sneaking up on here? We have a random variable. We have values of the variable that are likely and unlikely, likely and unlikely, and we have an expected value. These are the ingredients for a probability distribution. So p hat has a probability distribution. So let's talk about that because this is the big deal for today's lecture. And I'm going to put this up here as a fact. P hat has a probability distribution. I'll give that an exclamation point. And this probability distribution is called the sampling distribution for p hat. And I want you to keep in mind that even though we're calling it a sampling distribution, it's a probability distribution. So all the things that we've been talking about for probability distributions are still lurking in the background. It has to show all possible values of the variable and the probability of each of those possible values. And this is really, really analogous to our last lectures where we were talking about the probability distribution for x bar, which we called the sampling distribution for x bar. Both of these things are probability distributions for variables that are extracted from a sample. And that's why we call them sampling distributions. So what we have to do is see if we can talk about three key things for this. So here's the first question, and this is a critical one. Will the probability distribution for p hat be a normal distribution? And the answer is yes. Provided if our sample is big enough. So last time we were talking about whether the distribution for x bar would be normal, and we said yes if the sample size was large. When you're working with x bar, that means you have to have a sample size of 30 or larger under certain circumstances. But here I'm switching to the words big enough, because here it's not about 30. 30 is not our magic number here. And here's what we have to check. both must be true for the distribution to be normal. So what we're going to do to check to see if the sample size is big enough is that we're going to take the sample size and we're going to multiply it by the population proportion, the percentage of the population that has the characteristic. If this product is greater than 10, everything's looking good. It looks like the sample is big enough. But we also have to check and the sample size times Q also has to be greater than 10. So remember, what's Q? So if P is the percentage that has the characteristic, Q is the percentage that does not have the characteristic. And so you got to look at both of these. And if both of these are met, then you're good to go. You've got a normal distribution. So I'm going to put a box around this because this is important and we need to have easy access to this. We need to be able to find it as we're learning about this. Okay, so that's the first thing that we need to talk about for this probability distribution. The next two things hopefully are predictable. We need to talk about the mean or expected value for p hat, and we need to talk about the standard deviation for p hat. So let's get into that. I'm going to go ahead and erase this because I need the space on the board. But I'll stick with our lettered list. So let's talk about B in this list. What about the mean slash expected value of p hat? All right, and this is really cool. I like this a lot. Now, we know that if we're working with probability distributions, we're talking about the mean, our notation is mu. But I can't just use mu. As we saw in the last lectures, mu is already taken by the population, so we bring in a subscript. So it's going to be mu sub p hat. And so we're talking about the average of the p hats, or the mean of the p hats. We can also use this notation, the expected value of p hat. This notation is not very common, but I like it. I really like the idea of expected value. If you get on board with the idea of expected value, it's going to pay dividends for us as we go through this course. And here's the thing. Don't overthink this. This is really important. Because let's go back to our last example, where 62% of the students had a part-time job. What would you expect to get for p hat? And we said 62%. And that's a huge concept that the patterns that are present in the population should carry over to our sample. So what would you expect to get for p hat? I would expect to get the percentage that's present in the population. Or on average, I would expect to get a p hat that's the same as the population proportion, namely p. So once again, this is not intended to be a computational formula. This is just a statement about how stuff works out. So I'm going to put a box around this too because we need to keep track of this. All right, now here's the really cool part, is the idea of standard deviation. So the standard deviation of p hat. Now remember, the standard deviation always talks about spread. And here's the good way to think about it. We have an expected value. We've got a nice normal distribution. We've got an expected value right in the middle. And what this standard deviation is going to capture is how far away, how far below that expected value and above that expected value are you willing to go before you say, that's weird, that shouldn't happen. So that's what this standard deviation is going to capture. Of course, the notation for the standard deviation is going to be sigma, but again, we have to make sure that people understand that we're talking about p hat, so it's going to be a sigma sub p hat, bringing that subscript again. And this is simply calculated as the square root of p times q divided by n. And it's important that you write this carefully. This entire fraction structure right here is under that square root symbol. The square root symbol covers the entire fraction. So I'm going to put a box around this too, because we'll need to grab a hold of that in the near future. And this, I think, is worth noting. Remember that p plus q has got to be equal to 1. Because in this situation, either somebody has the characteristic or they don't. P is the probability, or sorry, the percentage that has the characteristic. Q is the percentage that does not have the characteristic. Those two probabilities or percentages have to add up to 1. So that also lets us make a somewhat useful statement that Q is 1 minus P. So we'll keep track of that. Okay, so this is really cool because we now have all the ingredients that we need to go and take a good close look at the probability distribution for p hat, or this sampling distribution for p hat. We know under what circumstances it'll be normal, we know what the mean or expected value is, and we can calculate the standard deviation. So I want to go into some actual numbers, a specific example, but I'm going to pause this video here and pick up a couple examples in the next video. I'll see you soon.